three level order traversal. Given the root node of a binary tree, return the order level order the traversal of its nodes values from left to right, level by level. So just easily looking at this, we can tell that this is going to be a BFS sorting method. So let's copy this. B blep first searcher BFS for sure. BFS. So now let's look into the problem more and more. So we're going to return these values, return the level or the traversal. Simple. Let's take return. Perfect. So now let's look into the examples. So in this example, we have this three, and this is our first level, second level, and third level. So we have three, and this one, and this one. So this is our root node, and we start with this one, and we have to go down. Since this has a left child, right child. These siblings nodes will be added. This one will be added alone, and this siblings node will be added after it, and this one, and the children of these ones, sibling nodes of these two, will be added last. So in this case, we only have one root. So so our output will be one. So now let's look into this. So this one is, we don't have anything here. So let's take care of that first. Nothing. Return nothing. Done nothing. If nothing. There is no root. So now let's look into it. If root is none, return none. So now let's we use a queue for this method of searching through a three binary three. Q equals to a list, an empty, no, we'll put a root in it. So first in, first out, queues, our result. Let's call it output to be more descriptive. Empty list. So now let's make a while statement in case while we have a Q value. If we don't, then this one will take care of that. While Q, while we have a Q value, while we have a Q, return. No, while we Q. So hold on. Let's make our basic BFS statement without adding anything to the levels yet. So let's go for level. So for underscore for node in the range of the queue, the length of queue. Let's name this the level size so that we know, so we can be more descriptive. Level underscore size equals to this. And move this here. let's just go with our so let's, for every node in it, let's pop it out of our queue dot pop 0 first value to first in first out. That's how queue works. And let's assign it to our node variable. So now, after popping this thing out, after popping the first value out, let's add it to our level node. So levels node in levels node level underscore node nodes. Should I call it node? No, I'll just call it node. Level node. And then make it leave it empty, and then let's add it to it. So level node underscore node, the append node to it, append a node to it. So for every node in it, append it. So now let's add the children node to the queue. If we have a node that left, let's add it to the queue dot append node dot left. If we have a node dot right, queue dot append node dot right. So now, after we do add this, the value, we need to do the values of node's values, not just the node. Underscore node values. That node values. The val that's defined over here. So now let's add them into this. So after we're done popping them out and adding them to the level, to this level over here, let's add them to this, to the result output. So let's get out of the for loop. So the append dot node level underscore node and the return this. I'll put that this. Now let's see if it's going to work out properly. So level up. And it did work out, yes. And our space and time complexities are O of n. So every node will be added to it. So it will get to every single node, adding them to them once. And also our space complexity is also O of n, because every node will be added to a list, So both space and time complexities O of ends. And that's it for this one. Let's submit it and see if it works. Yes, and it passed all cases, and that's good enough. And that's it. This is using our BFS method, and it's somewhat easy, not too hard. If you understand BFS, it's easy.